And let me introduce a speaker. So Professor Sanmi Koyejo is currently an assistant professor in computer science department of Stanford University. Before that, he was an associate professor at UIUC, where I was very fortunate to work with him as a postdoc. Sanmi currently leads the Stanford Trustworthy AI Research Lab with a focus on applications to neuroscience and healthcare. Sanmi has several career awards and best paper awards, including the 2 recent outstanding paper awards from NeurIPS. Without further introduction, let me hand it over to Sanmi. Yeah.
Thank you, Jen, for the very kind introduction. And I think good memories for me as well from working together at Illinois. So excited to be able to visit the other way. So I'll present a paper that we, I guess, put on archive last year and then eventually published at NeurIPS, which I think has been interesting in terms of its reception in ways that maybe we didn't predict. I'll mostly focus on the scientific bit, but I'm also happy to talk about some of the reaction to this as we go through and as people might have questions. So I should highlight that this work is with incredible PhD students that, in fact, as always, when professors speak about research, most of the actual work is done by students who are sort of smart, creative, hardworking folks, sometimes postdocs. And so here I want to just highlight Rylan and Brando, who did an incredible, meaningful amount of work to get this work off the ground. So I'll start off with a simple summary of the main results. So there's existing knowledge in the field, and sort of, if you like, one of the key scientific claims that drives modern AI is that scale typically has a positive impact on model behavior. So large language models, I think, are focused right now, but I think this claim is true, or seems to be made in general about building AI tools. This idea that models tend to improve at scale. Scale here could mean some combination of parameters, data, computing in various ways. And for instance, as you might know, there are papers, for instance, highlighting things like scaling laws, which are attempts to quantify exactly how scale affects model behavior and sort of investigate what happens explicitly, usually experimentally, what happens if we allow more and more parameters or data or computing. So based on this broad argument, I think some have suggested a narrower, more pointed argument, suggesting here that improvements in large language model capabilities, so how good the model is at a variety of different subtasks, can be unpredictable. So the argument here is small models are bad at many kinds of things. Big models tend to be better. I think the key component of the claim is that this change from small to big seems to happen unpredictably. And I'll give some examples of some of these claims in literature, and also the extent to which there is a precise definition of what emergence might mean. So emergence is one of those words, like many words in science, that has a colloquial meaning. So, we generally think of emergence as something changing or something appearing. And I think the colloquial meaning may be fine. I think, though, the argument I'll make here is to the extent that there's a precise definition that's scientific, there's some gaps in that definition. And some of what this paper is trying to do is ground some of the claims that are being made and help understand which the science supports and which doesn't. And so, in particular, we argue that many of the claimed emergent abilities are either predictable, so existing knowledge provides enough signal to tell whether the models will get better and when and where and how, or if we just do better statistics or other measurement types or other metrics, we can get a good signal about the behavior of these models with scale. That's the main story in this paper, and I'll mostly talk about this paper. At the end, I'll maybe touch briefly on some of the other work that we've done, and a little bit on the broad direction of the lab to the extent that there's interest there. So as mentioned, we're fortunate to be recognized by the community. This is one of 2 outstanding paper awards in the main track of NeurIPS last year. Very excited about this, and I think this has helped with some of the attention this work has gotten, and the opportunity to discuss this with you and many other people. It's also available in archive, so if you're interested, there is an archive version. There's also a NeurIPS version on Open Review that's freely available. So I think easy to find the paper and maybe read into the claims in more detail. So a little bit of background. So emergence, again, this is comes from intuition, at least in scientific venues generally. It comes from this intuition that has been seen over and over again, a lot in the physical sciences, some in the chemical sciences, that often more is more than more, if you like. So more can be different. And sometimes various things that we may be studying or interested in can change meaningfully, sometimes unpredictably, in terms of the effect of, in terms of scale. So I think one salient example, and one that's often noted, are examples from physics, things like sort of radioactive materials, some like uranium, for instance. Many of you might be familiar. If you have a few molecules, you have some radiation, but you don't necessarily have critical mass. But once you get above some critical mass, it becomes something meaningfully different. It goes from maybe something somewhat dangerous but contained to something that ends up being quite a bit more dangerous. So again, if you're familiar with how like large-scale nuclear events happen, a lot of this ties to the effect of having lots of uranium molecules all in the same place. And so the idea here is that as the complexity of a system increase, you might have new properties that manifest themselves. And I'll highlight that one salient part of this claim is generally the argument that says that these new properties cannot be predicted or explained, so happen sort of unpredictably, even if you have a good quantitative understanding of the system at small scale. So again, it's this idea that in complex systems, small to large scale is different in a way that sort of there's a meaningful gap, and our knowledge of the small scale can't really tell us anything meaningful about what to expect at large scale. So again, prevalent idea in science, lots of examples of this. So this is for sure a real thing. For sure, this is a real thing as well in many areas of machine learning and statistics. Some of you might be aware. So for instance, Jing and I worked on like recovering sparse signals in high dimensions. And there's known theory on sample complexity bounds that roughly tells you below some sample level, you can't recover sparse signals. Once you get enough samples, quote unquote, suddenly you see that the rate of success of recovery goes from effectively 0 to a very high, effectively close to 100% with the right algorithm. So things like this are known. It seems to be a sort of recurrent phenomena. I'll highlight here, or I'll anchor here strongly on this unpredictability thing, because I think most of the discussion today will be tied to that part of the claim. Again, if you like maybe older quotes in history on this, there's again, this is an old idea. So this idea from Aristotle that the whole can be greater than the sum of its parts. So this is an idea that comes around quite a bit. Within machine learning, and particularly language models, I think there's been some good work in the field trying to ground this idea. Some of these predate to some extent, even ChatGPT and related systems and tools that have had such a meaningful impact on the field. Again, this idea within the field has been percolating that sort of as scale becomes one of the main drivers of what systems are doing, our systems might just be very different at sort of large scale versus small scale. So I'm showing here a blog post from Jacob Steinhardt at Berkeley, just trying to highlight this idea, focusing on machine learning systems and the effect of scale. So partially motivated by these observations, there's been quite a bit of work looking at the behavior of or the quality of models for various kinds of tasks as scale increases. So I'm showing here an example. This is from 2020, looking at addition. So there are many reasons addition is interesting to study, but here the task is I give you, for instance, 2 digits, 19 and 25, for instance, and I ask you to input this to the model, and the model is asked to respond with the sum of those 2 digits. So this is something you might do with a calculator. Now you're asking a language model to do this. This is interesting for many reasons. One, it's thought to be doing arithmetic is thought to be tied to reasoning. So, to do arithmetic well, sort of you need to be able to understand an algorithm, or we think it's required to be able to understand an algorithm, at least to do this, compactly and at scale, such that you sort of correctly, for instance, carry over numbers when you add 2 digits together. And this carryover idea, again, and this sort of algorithmic aspect of it is appealing because we think, as a general field, reasoning is one of the key aspects of intelligence. And we'd like to build models that we think can reason. And so there's been a lot of interest in addition as a precursor to this. And so understanding how well models can do things like addition. So all the way back in 2020, this feels like a lifetime ago now, but there's already a lot of interest in trying to understand these kinds of questions. So in 2022, Anthropic also wrote a paper here interested in predictability of the behavior of models with scale. So they looked at addition once again. They also looked at what has become one of the main benchmarks in language modeling fields, this MMLU benchmark, which has a bunch of tasks, many of them tied to reasoning, and also questions like, or models that do tasks like program synthesis. In all these settings, the goal is to evaluate how well the model does as number of parameters grows, to understand the extent to which we can predict model behavior with scale. I think a lot of the, I guess, part of this space in terms of like labeling and definitions, some of it also came from work looking at the extent to which models could solve things like modified arithmetic task, logic-based tasks that involve, say, word unscrambling or repeat copy, things like figure of speech detection. Again, here, the goal to understand how the behavior of the model might be correlated or might be related to the scale. And here, I think some things to keep in mind is the sort of zero behavior till you hit what feels like a critical scale, and then all of a sudden, the models get better. And they also coined this term breakthroughness as a measure of sort of the extent to which you expect a model to have this flat zero performance to something that looks suddenly like much better performance. The term emergence itself, in terms of like defining it and it being used within the machine learning parlance, a lot of it came from a paper in 2022 that looked at a bunch of different language models at the time, things like GPT-3, Lambda, Go for Chinchilla, and then evaluated how well they did on a bunch of tasks, things like arithmetic once again, but also other tasks like unscrambling, questions in different languages, transliteration, various tasks like this, and asked again, what do the model behavior performance look like as I increase scale? Okay, so again, there is this converging sequence of evidence or increasing appreciation and interest in this idea that some aspects of model capabilities, or sometimes called abilities, are meaningfully different at large scale in a way that's unpredictable from small scale. And this is part of the definition that came out of this emergent abilities paper that I just discussed. And in particular, one of the key aspects of their claim was that you can't simply predict what will happen at scale by extrapolating what happens at large scale, simply by extrapolating what happens at smaller scale models. And this captured the imagination of the field. Again, particularly with the more recent work that has tried to make some of this rigorous. Particularly folks who are worried about, say, AI safety are quite sensitive to this, because if models can get better in unpredictable ways, this suggests sort of unpredictable behavior models that can be worrying. I'll pause briefly. There's a question. I can answer that question.
Yeah, I need to ask the straw man question. I've heard emergence described as nonlinearities in bulk properties, typically of a statistical system.
Mm-hmm.
So are these curves actually nonlinear? I mean, they look exponential, but the x-axis is logarithmic.
Yeah. I think that's a meaningful point. The nonlinearity, so short answer, I think in the right scaling, I think you're right that the strength of the phenomena seems less striking. We'll talk a bit more about this in a little bit. So I'll defer parts of your question to when we dive into some of the results. But I think you're already noticing part of maybe some of the weaknesses in the claim that, again, the strikingness of the observations partially tied to the scaling that we're using for the x-axis. I think that's true. I should also say that I think I'll focus a lot more on the predictability aspect, but this will also couple with some of what you're saying. I think one of the challenges, as I mentioned briefly earlier, is that emergence, the nature of the way it's being used in the field sometimes mixes some precise definition with colloquial definitions. And in particular, even like the precise definitions have many different ones across different ways people are talking about things. I think this is true of many aspects of modern, large models and AI systems, is sometimes lack of preciseness in what people mean when they say something. Here, I think we took a definition that people seem to somewhat agree as at least meaningful for what might be worrying long-term about models, if true. And I'll mostly anchor on that, but your point is very well taken. I think great question.
Okay, sorry to knock you off track. Let's get back on. We're enjoying
No,
this.
I appreciate the question. I think it's meaningful, and we'll touch on some of this as we go along. So again, specifically this idea of sharpness. So models sort of seemingly getting better in what looks like an exponential increase. Unpredictability is often of concern, to the idea that we know the scale matters, but we don't know when the scale effect will kick in, and suddenly the model will get better. And if we can't predict when this happens, I think this might be cause for concern. And so we asked some research questions. If this is true, this immediately suggests thinking about questions like what controls which emergent abilities will emerge, and what controls when these kinds of what you might call emergent abilities will emerge. And you might want to think of the sort of pro-social version of this. If we're building algorithms, methods, tools, what can we do to make some of these emerging these abilities, the ones that we think are good, how can we make them emerge faster? There's also a maybe safety aspect of this. Parts of the models that we think we don't like, are there ways to make them less likely to emerge? So that's, again, the premise for all this. Where we come in, and what this paper will mostly focus on, is a critical reevaluation of the setup papers that have tried to make this claim about emergence. And we'll go from maybe the general story to a precise, the actual experimentation that's been done, and then try to understand the extent to which the claims being made more broadly is supported by the specific observations that have been made. So, again, to belabor the point, emergent abilities seem to appear at scale. One observation that led to a lot of this work, I think this was Ryland's observation from, maybe interestingly, one of the classes he was taking, was that the choice of measure seems to matter quite a bit, and whether or not the behavior that we see qualitatively seems to have, as described briefly earlier, this idea of like exponential scaling behavior as I increase scale. So in particular, as I'll end up spending quite a bit of time on, we found that, one observation that sort of immediately becomes apparent is that metrics that are nonlinear or discontinuous seem to make this phenomenon stronger than metrics that don't have these properties. And I'll try to be a bit more precise about this in a minute. So in particular, if you look at the Big Bench paper, the vast majority, more than 92% of the abilities that they called emergent in that paper, are under two particular metric choices. One metric choice takes the model prediction, looks at the probability that it assigns to different potential tokens. This, for instance, shows up a lot in MMLU kinds of tasks, where the probability of, you have like a 4 or 5 potential, typically 4 possible answers, and the model probability assigned to any one of those 4 possible choices. You just look at the max of those probabilities, and it's a 1 if it assigns the high probability to correct option, 0 if it assigns the correct probability to, or it assigns the highest probability to the incorrect option. So this is a metric that looks at the probability of different tokens within the model, and he uses this to make an evaluation choice about whether a model is good at a particular task or not. There's also exact string matching. So this is related. Here, you're not using the probabilities or tokens, and here you're often using this in settings where you're making sequential predictions, so multiple tokens being predicted. So exact string match, this is an accuracy kind of measure. This gives a score of 1 if the output string is exactly the same as the target string. So you can imagine, for instance, if you're interested in addition. In addition, you will check whether you give it 2 numbers, you ask for the addition of the 2 numbers, you get a 1 if the 2 numbers, the answer is correct, you get a 0 if the answer is incorrect. So the vast majority of what are claimed as emergent abilities occur under one of these 2 metrics. And so this suggested to us that perhaps the metrics are playing a big role here. So we wanted to investigate this further. And so we posited a simple alternative explanation. So again, it's sort of reasonably agreed across the literature that there's this linear on a log-log scale, so this exponential decay of sort of cross-entropy error as I increase some notion of scale in models. So this is effectively the scaling law, but written in cross-entropy with log-log as opposed to linear. But again, this is supported enough empirically that this is sort of thought to be a stable phenomena for many large models. And so we made a simple hypothesis and said, suppose all of these things are mostly driven by sort of token error. We're going to use this token error to come up with a very simple model, and then see how different choices of metrics interact with token predictions based on this sort of naive model. So this naive model sort of accepts the power law behavior, so this sort of scaling behavior of cross entropy. So how likely am I to predict the next bit correctly with scale? And then asks, how do, for instance, exact choice metrics or exact match or the other sort of token probability metrics, how do they behave under a simple sort of synthetic generative model where the only parameter is how likely am I to get the next bit correct. So in particular here, we're ignoring the sequential notion. This is, again, a intentionally naive model that only looks at the probability of getting the next token correct as the main parameter of interest. And so if you like an x-axis. So instead of the x-axis being model size, it's sort of taken as gospel that model error will scale in this sort of parallel way with model size. So if you look at, again, just repeating the same thing, but if I look at cross entropy under the naive model ignoring sequence, I can immediately pull out a probability of getting the next token correct. The curve looks exactly like you'd expect. This is just e exponential of this log thing. And so one potential alternative explanation, if you're at least convinced by the observation that the metric choice seems to be a key determiner, is suppose I choose a metric that has a nonlinear scaling with the token per token error rate. So an example is if I'm interested in this like 2k digit integer addition, I'm going to give a performance measure of 1, so accuracy of 1 with exact match, 0 if I have sort of any error in anywhere in the string. And the claim here is that I should be able to predict accuracy on this somewhat more complex task of k-digit addition using simply my knowledge of the sort of aggregate statistic of how well the model makes next token prediction decisions. So here, again, I'm repeating again, but I want to highlight that I've taken this somewhat complex task of addition that we think nominally involves some notion of reasoning, for instance, and complex arithmetic. We've reduced it down to we've taken away all the frills. We're just going to look at how likely is a model to make the next token decision correctly, and entirely using this, try to understand how this measure might behave for, say, an accuracy metric for k-token prediction. I'll state this out in more detail in a couple of slides. Alternatively, instead of using this nonlinear style metric, if I pick a metric that allows for linear or smoother scaling with token error rate, I would expect the predicted error or the effective accuracy of the model to have much more like well-behaved standardized behavior. So much more well-behaved, much less exponential scaling kind of behavior. The argument here is that the nonlinearity or the sharpness of the metric is having a big effect on the observed phenomena and our inference from this, how much we think we have unpredictable changes. Very similarly, if I do the multiple choice, picking from k choices, here, say 2 choices as possible options. I'm going to just anchor on, so my answer is going to be the highest probability mass. Similarly, we're going to make a similar claim. If I have this kind of discontinuous metric, the claim here is that I should expect what looks like sharp behavior with the discontinuous metric. However, if I have a continuous metric that doesn't have this sort of sharp thing, so in the multiple choice case, I'm still looking at probabilities, but if I go from argmax probability to something that looks like, for instance, the Breyer score, which is the error of the probability average over a population, this should behave much more predictably and sort of much less emergence type phenomena from that kind of metric. So I'll just put all this together in terms of the main claims. One of the main claims, we'll touch on some other ones here. But again, starting from how well we think models' error should behave as I increase scale. There's a general observation, models get better, their sort of error behavior as measured by cross entropy generally gets better. I'm going to posit a naive model that just ignores the fact that I'm doing sequential prediction. Just look at this as my likelihood of making the correct decision for the next token. So I can easily convert from cross entropy under this naive model to a probability of error for the next token. And I'm going to have some scaling curve there and argue that this is sort of the expected behavior of models with scale for probability of next token prediction. Now I'm going to construct some meta task, which is either going to use something like accuracy or multiple choice grade. And the argument is, if these meta tasks are measured with a nonlinear metric, I should expect to see something that looks like emergence type phenomena. If these meta tasks are measured with something that is a bit more linear, I expect much more predictable behavior. And I'll leave to the end maybe some discussion of why one or the other setting might be much more attractive when you're trying to build or evaluate models. So do I care more about maybe predictability of model behavior with scale, because I can actually tune and optimize based on scores that are non-binary, if you like, versus other choices of metrics that lead to what look like unpredictable behavior outputs, but I'd argue may not be foundational in the sense that the metric choice is playing a big role in the observations and the inference from those observations. So this summarized the explanation is perhaps there are no sharp or predictable changes in model behavior. We can attribute this, what seems like this observed change, to one of three factors, either using a metric that's sort of nonlinear or discontinuous on the token error rates. I haven't talked about this yet, but we'll spend some time on signal to noise ratio type behavior. So I'll argue that part of the reason why we see what looks like 0 at small scale and then much bigger, almost saturation at large scale, ties to the fact that we're not actually getting the right signal amount at the small scale. And if you've done signal processing, it's sort of well known that if you have low probability events, you need to sample more. And we'll argue that part of the reason we're not getting the right measurement at small scale is that sampling is not done sufficiently to actually correctly get the signal of what's happening at small scale. And similarly, sometimes the phenomenon is tied to insufficient measurement even at large scale. So this is the main hypothesis of this talk. We've sort of built, I think, over a few slides to this, hopefully clear in terms of both the motivation for this work and, again, the main claims that are being made as an alternative explanation for the phenomena. So, we are going to try to back this up with a bit of evidence. To this end, we looked at a few of the existing models. So we looked at the time, this is mid-2023, but we looked at OpenAI's GPT family of models at different sizes on integer arithmetic tasks. And these are tasks where the emergence phenomena had been claimed from existing papers. We looked at, I apologize here, it should be 1, 2, 3. I think my PowerPoint is something with the spacing got a bit aggressive. 2, we also looked at meta-analysis of metric choice on Big Bench, which again was one of the papers that claimed the emergent abilities. And then we looked at toy networks on vision. And the goal here is to really anchor on or emphasize the point that we're trying to make. So in the vision one, we're going to look at completely new tasks where no one has claimed emergence in the past. We're going to choose metrics that are different from what people normally use, and we'll show how choosing the metric actually leads to what seems like an emergent phenomenon as matching existing claims in the literature, even though the main thing that has changed in those settings is a metric choice as opposed to something meaningful about the model that's being built. So under the hypotheses that I claimed, the sort of story that I said earlier, what you would expect, so predictions for arithmetic tasks, is that if I use accuracy, some sharp metric, versus using a soft metric, so for instance here we looked at string edit distance, which is counting the number of mistakes across the string, versus overall accuracy, you should get much smoother, continuous, predictable behavior as I scale models. Second, we looked at more sampling. So the claim here is, if I sample much more at small sizes, so I just increase the resolution of model performance, I should also see much more smooth, continuous, predictable improvements compared to even on the original sharp metric. And then third, if I look at whether or not I'm using a sharp or soft metric, if I increase the string length, I should see predictable change in the model behavior as a consequence of the number of the length of strings. And in particular, if you believe this very simple probability model, which is just I'm looking at how likely I am to get the next token correct. From this, I can immediately work out with basic probability how likely I am to get 5 tokens in sequence correct. So if I know, again, this is under a simple ID assumption, I'm looking at how likely I am to make one mistake. I can use this to work out just simply by doing the product of the probabilities, figure out how likely I am to make k mistakes, say 5 mistakes in a row. And this should be able to tell us something precise about what to expect in scaling as the length of the tokens gets bigger, because we know, again, from basic probability, how single mistakes can compound under this very basic assumption. So first claim, this change in metric go from nonlinear to linear. So we did this experiment. So again, this is the hypothesis. This is under the simulated model. Here I'm looking at accuracy as I scaled number of model parameters. Again, I have a phenomenon that looks exponential, if you like, even with, again, to your point in the earlier discussion, I have a log scale on the x-axis, but I'm seeing this, what looks like nonlinear increasing performance. I'm going to go from this nonlinear metric to something that is linear, something like token at the distance. I see much more predictable behavior of the model as I increase scale. So that was on a prediction under a simple model. I'm looking at the real data to see how well the real data matches our prediction. So as you might expect, given that I'm presenting this paper, we look at the results for different string lengths. So 2-digit addition, 2 4-digit addition, all the way from string length of 1 all the way through 5. And we see, again, if I use accuracy as the metric, we get exactly what has been shown in existing work. If I use token added distance as a metric, we get the alternative observation, where even though the theory is using a very, very impoverished prediction. So this is the theoretical model here is ignoring sequence correlations. It's just saying how likely am I to get the next token right. Yet we find qualitatively the same main effect, that you get sort of much more predictable behavior with scale compared to using this sort of nonlinear accuracy metric versus token added distance. Similarly, you can look at multiplication, you get a similar kind of effect. Again, sharp versus soft metrics on real data, on sort of real experiments, you get much smoother, much more predictable performance with token added distance versus what looked like sharp behavior if I use sort of accuracy as a metric. The second prediction, as mentioned briefly, is if I increase the resolution at small scale, I should be able to better disambiguate signal from noise. And so we check this out. Again, the idea is that part of the reason why we see what looks like this sort of 0 to really good performance is that we're not actually measuring the 0 part well enough. And so we looked at things like the 4-digit addition. I apologize, I think I have incomplete slides here. But in the paper, and briefly mentioned here, we again are able to look at sampling at small scale much more. And the main sort of takeaway from here is that at small scale, we see instead of 0 to like the sharp performance, we see much smoother change in model behavior from small scale to large scale. I mixed up the slide slightly. I apologize for this, but I'll maybe defer to the paper on looking at sampling effects. So sampling much more at small scale leads to much more predictable behavior. You're not seeing 0 at the small model sizes. You're seeing noisier, smaller signal behavior, but one that we could actually measure if we just sample many more examples. Okay. Next, we'll look at Big Bench, which is Google's benchmark for large language models that has already looked at a bunch of emergent phenomena. Our claim here on the Big Bench is that if the metric is not the main phenomena, then we don't expect to see any interaction between the metric that you chose to use and whether or not you claim emergence from the experiments. Also, we did a sort of somewhat interventional evaluation here, where we looked at the same task. We changed the metric from a sharp one to a softer one, and asked whether the emergence phenomena remains when I change the metric from one to the other. And here, we look at some quantification. The Big Bench paper in particular tried to model what emergence might look like. And so they suggested metric for emergence, which roughly tries to capture sort of how much does the model scaling deviate from some median prediction. So that's one way to read what this metric is showing, is that sort of the median prediction you'd expect to look roughly, as I change the x-axis scale, I expect the model to, the deviation of the model performance with scale to look a bit like it's median, so smoothed median. And you're looking at how much the scale of the model is sort of much more dramatic than smoothed median type curve. So that's what this metric is meant to evaluate. And so based on this metric, they looked at a bunch of different tasks and different metrics. So for each task, they have a bunch of different, for instance, BLUE score, which is sort of a well-known score for language modeling tasks, accuracy, various kinds of bias scores, fairness scores. So this was a comprehensive evaluation. And we looked at the percentage of metrics that show emergent abilities, and we found roughly 10% of the pairs of models and tasks show what you might claim as emergent abilities. And in particular, just to turn this, say this directly, 35 of the 39 Big Bench metrics don't exhibit emergence. Of the tasks where you see emergence, most of them, 76%, use this multiple choice grade that I already described. So this like probability mass on the right result. And about 16% use exact string match. So, you know, combined 76 and 16 is sort of in the 90s of the fraction of tasks where the emergence is claimed is one of these two metrics that I mentioned briefly. So we looked at the existing models in Big Bench. And here I'm showing what happens if I just play with different, we're ablating, doing some ablation over the number of shots. So the number of times you query the model to try to get the right answer. So you pick, say the answer is correct if it gets the answer correct in one of k tries, 2 or 3. And what we show here is if I use the multiple choice grade, we see what looks, again, this is a little bit messy because these are sort of highly empirical and less smooth. But here, if you evaluate using, for instance, the Big Bench emergence score, so their quantification of what it means for a metric to be emergent, you see emergence for multiple choice grade. You don't see something that looks emergent for Breyer score. So you see much more linear predictable behavior on the same exact task, things like irony, identification, sports understanding. But the main thing I've changed is I've gone from this sharp metric of multiple choice grade to a softer metric of Breyer score. The final experiment we did to close things out is that we looked at, we created a new, well, we looked at a task in vision that has been studied quite a bit. So I think in language, the reason this is so fascinating is that this seems new in a meaningful way. So, I mean, we expect model behavior to change with scaling, but language seems to be the first time that we've seen this and interpreted the results in this sort of sharp, emergent way. So this really does feel like a new landscape than what we ever saw in any of the existing machine learning tasks. And so to really highlight this metric choice effect in claimed emergence, we looked at a vision task where there haven't been emergence claims. So here we look at a simple autoencoder type reconstruction task. So I build an autoencoder. I look at the mean square error of the quality of the reconstruction. So this is a metric that rewards how close the reconstructed image is to the original image. It's using mean square error. It has sort of what you might expect, which is sort of linear scaling behavior of the error decaying predictably with model scale. And then we make a small change to the metric where instead of mean square error, we do this sort of identity function style of error. This metric says, if my error is within some small c of the truth, so if my prediction, my reconstructed image is between c of the truth, I get a score of 1. So I've correctly reconstructed the image. I get a score of 0 if I'm bigger than c away. So I've gone from what seems like a soft metric to, again, what seems like a harsh metric. And here you see what you might predict based on our claims. So you go from behavior that looks sort of linear and predictable. I should change the scales here so that they're all the same. But the main qualitative finding is here, which is, with a metric that allows for partial credit, we see predictable changes with scale. With this metric that only gives credit if you're c close to the truth, you see what looks like emergent phenomenon in a setting where there have not been any claims, because again, this seems special to language and the way that we've scaled language models. The argument here being that, again, the metric has a big choice in our interpretation of the results, in addition to the claims already made about predictability, just highlighting this metric choice effect. And we have a few more examples in the paper of sort of similar phenomena, similar kinds of experiments. So I'll conclude here, maybe talk a bit about limitations and a bit on sort of broader aspects of the work. So, in general, models are known to improve with scale, as mentioned already, parameters, data compute. Within the field, there's been a lot of interest in the extent to which some of these scaling behavior models for some choices of metrics seem to be what we've called emergent. I think here, thinking primarily about this sort of exponential change in performance in an unpredictable way, as a somewhat semi-precise definition of what emergence might mean. And in this paper, we argued that many of these emergent abilities do seem quite predictable, either by using better statistics, so actually capturing the signal to noise much better, it's with particularly at small scale, but also in large, or using metrics, which you argue are metrics that are not as nonlinear or metrics that allow for partial credit. And we see meaningful differences in model behavior. I think this still leaves open what to do based on this observation. So part of this is to at least allow for scientific completeness. It's worth saying that our analysis was restricted by the set of models that we could query. So for instance, at the time, we couldn't query lambda models, so a lot of our analysis relied, the analysis where we requeried models as part of the investigation, focused primarily on models that we could actually access and do experiments with. I would say some of the experiments just used published results and looked at how different metric choices affect things. But I think that's a meaningful statement of a limitation in this setting. I think another meaningful aspect of things is, and a lot of this boils down to human judgment, and human judgment versus what we need to create better machine learning models may not be the same thing. I think I'm sort of willing to have some of that discussion, but I think it's possibly open in terms of metrics that are useful for just understanding what models are doing versus metrics that tie to how humans observe model behavior, which I think many would argue that we felt like models weren't doing useful things, and then we felt suddenly that models were doing useful things, and that feels like a sort of meaningful step change of sort of emergent types of phenomenon. And so this gap, I think, is part of what's leading to what we claim is at least this this issue with interpretation of the results and how we might interpret it. I think, for what it's worth, while I don't see any evidence to make this claim, I feel, I guess, the responsible scientific thing to do is to say, again, our analysis is limited. So based on current claims of emergence, our analysis suggests that sort of the researcher choices have much more impact in the inference of emergence than sort of fundamental behavior about what the models are doing. And so the measurement is playing a huge role in the inference of emergence. Again, I'll leave open the possibility that there's some things that we haven't measured that matter. I say this with sort of scientific skepticism, but also allowing, or at least stating explicitly, that most of the evidence out there in the literature doesn't actually support that. Again, there are sort of unpredictable aspects of models that we shouldn't expect to be able to predict from small scale. Okay, so that's that on the talk. Very briefly, I'll just, unless there are questions, I'll just sort of touch on a few other things that my lab is doing that I think might be interesting, and I'm happy to have further conversations about. The other paper that we were fortunate to get recognized at NeurIPS was work with awesome colleagues at a bunch of different places, out of U Chicago, Illinois, Microsoft, Berkeley, a few other awesome places, where we tried to build the first framework for trustworthiness evaluation in GPT models. So this won outstanding paper award, but on the benchmarks side, so one of, again, 2 outstanding paper awards on the benchmark side. So last year was a good year at NeurIPS for me. But here we looked at various kinds of trustworthiness aspects that you might think are important in building widely deployed language models. So questions of things like toxicity, stereotype bias, various kinds of adversarial robustness, various aspects of privacy, demonstration robustness, fairness. I'm showing a few examples here where we, for instance, set up sentiment classification tasks and look at how models behave when there are small changes. So changes like changes in style, so going from standard English to maybe different dialects of English, adversarial changes in particular words. So going, in the first example, going from experienced to skilled, and how that might change model token probabilities. Adding backdoors, so adding phrases to text that might change model predictions. Questions of privacy, where we looked at the extent to which you could pull out PII from training data, in this case, within the models. Questions of fairness, so changes in model behavior if I change demographics or other sensitive attributes. And I'll leave to the paper to highlight some of the main inferences that we make, but I'll just mention that this is a toolbox that's available that you can sort of download, both from Decoding Trust or from Hugging Face, and sort of play with this if something you're interested in. More broadly, my lab is interested in thinking about trustworthy AI generally, and thinking about both foundational and applied aspects. So the role of data algorithms, I think we spent a lot of time thinking about metrics, as you might have seen from this presentation. And I think in addition to this, spent a lot of time thinking about the role of humans and how we define and evaluate and implement trustworthy AI systems. And of the areas, we focus quite a bit on questions related to bias, fairness, questions related to robustness of various kinds, security and privacy, and how all these aspects trade off with issues of capability of models. So to what extent are these sort of fundamental trade-offs? To what extent can we expect to get all these aspects of models to improve sort of uniformly at the same time? I'll stop here. I have a couple of minutes maybe for in-talk questions. And again, there's additional time after. I'm happy to discuss things further.
Any questions from the audience? Okay, Matt, please go ahead.
Okay, so first, great talk, thanks. Given that you're finding that performance scaling is smooth, given an appropriate metric, and possibly nonlinear, and that these systems are trained on vast amounts of data, and particularly for tasks like arithmetic, it's likely that all of the input-output pairs are in the training data. I wonder if you would comment on whether or not these systems are actually generalizing as opposed to memoizing.
Yeah, I think this is an excellent question, and related, though, not the main object of study here, but I think it's an important question of, if you like, data leakage in our evaluations, one that we're quite worried about. So I'll say a couple of things. One, we have started to do a bit of work precisely on this question. So what is the effect of what you might call data contamination on downstream performance? And classic, quote unquote, or maybe narrow, if you like, machine learning models, it's somewhat predictable. Like, you expect overfitting in a very predictable way. So you do, the more you train, your test data is in training, you expect to do better. And again, lots of both theory and empirical work showing what happens. And it's very predictable. We found it weirder in language models, where, so in particular, well, generally seeing the training, the test data tends to improve model behavior. It doesn't tend to improve monotonically so far. I'm happy to offline send a paper on arXiv that we started to study this phenomena. It's very weird in language models. So for sure, just to generally answer your question, for sure, data leakage is a problem. For sure, if I'm an adversarial player in this space, one way to get really high benchmark numbers is to just train on the test data, and I'll get really, like, at least better benchmark numbers than otherwise. There have been precise investigations of arithmetic specifically to check, can a language model do good arithmetic? Because I think part of the interest here, again, is can they do things that we think of as requiring reasoning? Because that seems to tie to whether or not reasoning might actually happen. I think so I guess I'm taking two aspects of your question separately. One is, like, can models do arithmetic? Two, data contamination. For data contamination, I think, mixed results in terms of exact effect, but it's for sure has an effect, and it's generally positive. It's just not nearly as predictable as in narrow settings. On arithmetic itself, the evidence so far suggests that generalization is not that good. So, it does well on the k digits addition or multiplication that it has seen. It does much worse on out of sample additions. I think it ties a bit to your point of, like, has the model seen all k-digit additions in training data? It's unclear. It's one of those things where I think humans are not actually good at, like, thinking through what is possibly available in training data in models. But it does seem hard, and there's actually quite a bit of concerted effort where people just train from scratch. For instance, work from Yejin Choi, where they tried to train from scratch GPT-3-ish size models for addition and just see how well it works. And it doesn't seem, the current evidence so far suggests it doesn't seem to get the algorithm right, because it tends to start doing badly out of sample, or much more often if I change from 2 to k digits. So this 2 to 5 digits, if it's trained on 5, will it do 6 correctly, for instance? If it's gotten the algorithm you think it should, I think often evidence suggests that it hasn't. So a bit of a complicated answer, maybe two-part answer to your question. I think a fascinating question, and so it has an interesting interaction with the rest of this ecosystem.
Gordon, please go ahead.
My question relates to the big bench analysis that you did, and if I followed correctly, you kind of were able to show that like 90% of the so-called emergent tasks could be sort of explained maybe by doing the partial credit metric, but maybe that would leave, like 1% of the 10%. I don't know, some small number of tasks
fair point.
Were emergent. Is there anything interesting in those to take away, or?
So I think this is a very valid criticism. I think part of the bottleneck here is that we're restricted to just looking at the results that they've shown, and if there wasn't a sort of obvious alternative metric choice within their experiments, it was harder to do this ablation to see what effect metrics have. I would say some of the open questions are to better answer for like a bunch of different cases. So for instance, one meaningful one, I don't recall if this is in Big Bench, but something like in context learning is not completely well explained by the analysis that we've done. It does seem meaningfully better in large models versus small ones. And I think it's been one of the pushbacks of some of the work is, is something like in context learning meaningfully different with scale in ways that we haven't explained. I would say likely yes, and this is sort of from extrapolation from our results. Maybe I'm doing the same thing. Just based on the evidence we have so far and sort of what this evidence leads to the intuition that metric choice is driving, or at least is a good explanation of, and you can imagine what this looks like for other kinds of phenomena where, again, you could easily change what you use it to measure. So I would say we don't have a complete answer. My strong bias based on the experience we have so far and the sort of the interventions we're able to do is to expect the answer to be sort of low signal in that direction. So again, matching the experiments, the inferences that we've made, but I allow for, there are potentially gaps. It's one of those things I think in this kind of work, like there'll always be yet another task, yet another metric. Part of our choice as a community is to decide what we think the main mode is and then do science to understand, I guess, to what extent we can cover the space. Very reasonable question, fully agree. And I think it's part of emerging work that or existing, using the word, but ongoing work that we're trying to understand better.